Now, there is another force that is acting on these ions, right, in this kind of an environment. And it's known as the concentration gradient force. Now, a gradient is just a change in concentration or change in amount, right, from one location to another. And we just described a gradient as it relates to charge, right? I'm suggesting that because of the action of this pump, you're going to get more positive charge outside and less positive on the inside. So there's a gradient in terms of charge. It's more positive to less positive, right? Well, you also have gradients in relationship to the concentration of specific ions, let's say, right? So if you look at, for example, sodium, there's a lot of sodium that's represented outside the cell, right? There's lots and lots of it. I want you to think about why, right? It's because the pump is kicking it out, right? It takes energy, it takes effort to mass sodium on the outside of the cell, right? There aren't too many places through, via which sodium can actually get back to the other side either, right? So that also, the impermeability, the membrane to sodium also sets up a higher gradient or higher concentration of, sodium on the outside versus the inside. You should look also that note also that potassium is in much higher concentration inside the cell, right? Again, that's a consequence of the pump, right? So there are concentration gradients that have been established here, and the concentration gradient force is literally the tendency for substances to move from areas of high concentration. So, for example, sodium is in high concentration out here, towards areas of lower concentration, okay? So if you have something with a great deal, or that's in great abundance in one location, and very little is found nearby, that substance is going to move, it's going to be pushed by this concentration and gradient force towards the area of lower concentration. And the reason, I always like to give a reason, but the reason is because, everything that has a temperature, right, is going to be moving. And you have a lot of stuff over here, and there are lots of these random movements, and they're going to be, largely extending away from the area that they're currently in. So they're going to end up moving, generally towards areas of lower concentration. So the idea, think about, if you're making lemonade or something from a packet, and you stick it inside, a big pitcher of water, right? It'll collect in one spot when you drop it in. Normally you stir it because you want to drink it, but if you waited, it would actually just distribute itself, throughout, the entire pitcher. It'll move from an area of high concentration, out to areas of lower concentration. So these are two forces, electrical, force and concentration gradient force, that are acting on ions and causing them to move in various directions. So if you look at sodium, for example, it's in a positive area, right? There's more positive ions out here, because you're kicking 3 positive ions out for every 2 you bring in. That biases the outside, right, to positive charges. Remember, you also have proteins on the inside, which tend to be negatively charged. So it is going to be more negative on the inside than the outside. So the electrical force is going to drive sodium inside the cell, right? It's going to want to come inside the cell. It's massed out here, going to be driven by at least 2 forces here, electrical and concentration gradient, to enter the cell, right? But watch potassium, because potassium is found in higher concentration inside the cell, right? And it's because this pump continues to pump it in, right? But the concentration gradient force will drive it the way it's being shown here with the arrow, right, out through these open channels. But think about the electrical force, right? Because it's a positively charged ion, yet the inside of the cell in a neuron at rest, right, this resting potential difference in charge, makes it more, or is more negative on the inside versus the outer. So these forces actually compete with each other at the resting potential. So the concentration gradient force wants to drive it out, the electrical force wants to keep it in. It turns out that at the specific charge difference, right, difference in charge, that we find at rest, in a neuron at rest, the concentration gradient force sort of wins out. It's a little stronger. So the direction of flow for potassium is going to be from inside the cell to out. Okay, but it won't, it won't leave as rapidly as that sodium will come in, right? Because in terms of sodium at the resting potential, right, the forces are aligned. The electrical force wants to drive it in. It's negative inside, it's a positive ion. And the concentration gradient force wants to drive it in. So the actual ultimate direction that ions will move depends upon sort of a summary, a summation of all these forces that are acting simultaneously. Okay. Now there's one more force, and it's a biological force. It's a force that you manufacture, right? It's this sodium-potassium pump, right? This is actually establishing the operation of this pump, which again is a protein that's generated based upon instructions, right, in your genes, right, and inserted into the membrane, and utilizing ATP, it takes energy to operate, is helping to establish these concentration gradients, right, by pushing sodium out and having it mass outside, and pulling potassium in and having it mass on the inside. It's establishing those sodium and potassium concentration gradients by its operation, right? And in addition, it's establishing or helping to establish that electrical gradient, right? Because it's kicking out more positive ions than it's bringing in with every turn, with every movement. It actually puts out one extra positive, every time it operates. So all these forces are playing a role in the neuron at rest.